group as the symmetry of 2 plus 1 dimensional black holes, at least at this value of k. What about higher values? Well, it's not hard to show that the coefficients in the Q expansion of the partition function can always be expressed in terms of monster dimensions. So it's conceivable that the monster is a symmetry of 2 plus 1 dimensional quantum gravity at every value of k. But I don't know how to show that this is true, or that CFTs with decleined partition functions do exist. Incidentally, if they do exist, then they're almost surely dual to pure gravity, since what else can they be dual to? We made sure they had nothing except anti-de Sitter space, the brown halo spectrum, and black holes. So, if they exist, they'd be dual to pure gravity, not to something else. There's a close analog of this in the supersymmetric case. The allowed values of the central charge are 12K, roughly speaking. There's a little sleight of hand that you can read about in the paper. Again, you can more or less uniquely determine the partition function by similar reasoning. And there are candidates for the right theories if K is 1 or 2, in this case. The K equals 1 theory was again constructed by Frankel, Opalski, and Lyman, and understood more recently by a student of Frankel's, John Duncan, only recently, while the K equals 2 theory was constructed by Dixon, Ginsburg, and Harvey by making a twist, so to speak, of the original FLM construction. The K equals 1 and K equals 2 theories have in common a discrete symmetry group that's smaller than the monster, but is again one of these sporadic finite groups, the Conway group. Well, I should have scrubbed this sentence. There's some speculations, but improved from this remark in my paper. So I guess I'm going to let you off the hook a little early today because I know you've been grossly overworked this week. Thank you. Yeah? Wormholes, in general relativity in general, wormholes are behind black hole horizons. So there are solutions that have wormholes, but actually from the outside they look like BTC black holes. What's that? From the outside you can't differentiate. Now, it's not clear what it means that there are wormholes behind the horizon. Now, Alex Maloney, actually, one of our members, has tried to interpret the microstates of the black hole in terms of quantization of the phase space of the wormholes. And there might be some truth in that. But at any rate, from this point of view, the wormholes are less black holes. That's true in general relativity in general, by the way. Yes, Michael? Yeah, right. Well, first of all, it's in general worse than you said. You describe what's called rational conformal field theory. There's the holomorphic one with one left and one right moving characters. There's the situation you described with finite characters of both kinds. And there's the generic situation which has no factorization at all. It has left and right moving versus arrow. So a priori quantum gravity in 3 dimensions could be one of those 3. I aim for holomorphic factorization because it's by far the simplest hypothesis, and I feel that a theory that's said to be said to be trivial ought to be simple. So I tried to guess what its simplicity was. I may have guessed wrong. But I did one little calculation that supported it, which was I took the gauge theory description at face value, and it gave that k left and k right were multiples of 24, and those were the values where my hypothesis was possible. Okay, so I could have gotten a different answer, and I would have, well, if the answer had been sufficiently different, I would have known that the hypothesis was wrong. Finally, there was one little bit of positive feedback, which was that the black hole threshold was natural. We didn't really put in the minimum mass of the black hole, but it came out, you could say. But you could also claim, by virtue of other things known about black holes and modular invariance in 3 dimensions, but that isn't really an independent check. You might want to look at the fairy tale paper to form more of an opinion on that. So, I didn't promise it's right. Yes?
So can you say a little more about what I know about holomorphic CFT at higher values of K?
About what the theory would be at higher values of K?
Yeah, are there examples of holomorphic CFT?
Well, there are all kinds of examples of holomorphic CFTs at higher values of K. But we need a lot more than that. We need what's sometimes called an extremal CFT, where there are no primaries up to dimension K plus 1. And there aren't examples of that which are known above K plus 1. That's the crucial ingredient. The way you asked the question, which was just for holomorphic CFTs at higher values of K, you made it too easy. There are bucket loads of those. One thing I'll say is that there is a paper that appeared on the web a few years ago by Yi and Gayato, who showed what's the genus 2 partition function at K equals 2 or 3 if the theory exists. So that might make it seem a little bit more tangible. A lot of nice formulas, and they kind of work miraculously. It's a pity if the theories don't exist. Yes?
It wasn't very clear to me if it had realization for the cosmological and something contradiction from...
No. The cosmological constant is, in SE2 gauge theory, the commutator of T plus with T minus is 2 times T3, and that number 2 is not normalized.
So basically it's like structural constant of the...
Yes, right. The cosmological constant here plays a role analogous to the 2. And Newton's constant isn't normalized because it turns into a Chern-Simons coupling. And in general, Chern-Simons couplings aren't normalized, roughly speaking. What the statement means is that they're not subject to infinite normalization. If you want to express a physical observable in terms of the Chern-Simons coupling, the classical formulas are not exact. That's sometimes described for some purposes as a finite renormalization. It's a different meaning, however, of the word renormalization. Yes? Well, it contradicts the fact that the theory has anti-de Sitter space. Anti-de Sitter space, one of the most important things I said, hopefully sounded trivial when I said it. It was aimed to sound trivial. I told you that the theory had a unique stable SL2R invariant vacuum, which had anti-de Sitter space as a classical approximation. If you accepted that one, then the Liouville theory is wrong, because Liouville theory doesn't have an SL2R invariant vacuum. And incidentally, although people often say loosely that Liouville theory is wrong because it gives too small black hole entropy, the actual answer really is that Liouville theory gives an infinite black hole entropy because of the Liouville zero mode. Liouville theory, unfortunately your question was one for connoisseurs. So I probably shouldn't be answering it in detail. But Liouville theory doesn't have enough oscillators to make the Bekenstein-Hawking entropy, but it has a zero mode with a nasty continuous spectrum above a certain threshold. And the continuous spectrum means that the entropy is infinite. So Liouville theory is maximally, well, I can't promise that a quantum theory corresponding to 2 plus 1 dimensional pure gravity exists. And if it exists, I can't promise it has, that it's a good model of black holes. For example, it could have long strings that Natty and I studied in a different context. And then the entropy would be infinite. And the spectrum